Greetings, geometry students. I appreciate you finding time to get your notes taken care of. Today we're going to continue on with a little bit of the reasoning discussion in a slightly different direction, and we're going to be looking at some measurement reasoning for the next couple of days. Our objective for these days will be to review the formulas and steps for finding perimeters and areas for various polygons and composite shapes. Now, as we move through this, a lot of it's going to seem like review, and a lot of it is review. So you may kind of be wondering, why are we taking a special time to look at a new lesson on this? Well, the reason is quite simple. Some of the ways that things like perimeter and area and even surface area and volume that we have been calculating and working on over the last several weeks, they can be questioned in some ways that we have not looked at, such as probabilities of hitting certain areas and stuff like that. So a little bit of a twist to it. Anyway, what we're going to be doing today is we're going to look at the basic diagrams. I'm going to have you get these diagrams into your notes, and then most of the math is going to be taking place in class. Okay, so here's kind of the setup of the problem that we're going to be looking at. So please copy this down. An aerial view of downtown Bronco, Texas, or Broncos, but just a made-up town. Bronco, Texas shows the shape of the rooftops of the buildings, and that's pretty much what you're going to get from an aerial view. When you are way up in the air in a helicopter, an airplane, or whatever, and you look down at the surface of the earth, nothing really appears to be three-dimensional. All you see is two-dimensional polygons basically looking back up at you. All you see is the rooftops. Okay. Now, what we're going to do is this fictitious town that we are working on, we're going to say it has an overall area of 750 feet by 600 feet. That's going to become important because inside of this area, we are going to have smaller areas. And based upon how the little areas compare to the bigger areas, then we end up with things like percentages. Okay, a certain building can take up a certain percentage of the overall area, and we can even work things like probability. What are the odds or the probability of hitting one of these smaller areas compared to the larger area? So it's important to know the overall dimension. Okay, and there are 6 buildings that we are going to place in downtown Bronco, Texas. Okay, so please copy down the diagrams. Okay, building number 1, when viewed from above, is going to appear as a regular hexagon, and the sides of this regular hexagon are 125 feet each. Press pause if you need more time to copy these diagrams. There's not a lot on each slide, so I'm going to be flipping the pages fairly quickly. Okay, building number 2 looks like this. Now, of course, it's a composite shape. It's a pentagon, but not a regular pentagon, so we would have to treat it as a composite shape, and there's different ways to break it down, but I've broken it down for you, and I am calling it a composite of an equilateral triangle and an isosceles trapezoid. Further, I give you measurements that the bases of the trapezoid are 125 feet and 75 feet, and the leg of the trapezoid is 150 feet. I will read that again for you in case you're looking at a small screen and can't see those words. It's a composite of an equilateral triangle and an isosceles triangle. The bases of the trapezoid are 125 feet and 75 feet, and the leg of the trapezoid is 150 feet. Okay, the dimensions of building 3 is going to be accompanying a circle. Okay, so we have a circular rooftop looking back up at us, and the measurement that you're provided is that the diameter is 200 feet. Building 4 is going to be pentagon shaped again, but this one will be a regular pentagon rather than the irregular pentagon we saw a couple of buildings ago. And our regular pentagon is going to have a side length of 125 feet. Building 5, rather strange one. Okay, we have an elliptical kind of shaped building with a part of it removed, an atrium. Okay, so the description I'm going to give you of this one is I'm going to say it's a composite shape. I'm going to say that the composite shape is semicircles on the ends of the building, a rectangle in the middle of the building, and then a rhombus removed from the center of the building. The measurements that you're provided are the dimensions of the rectangle are 125 by 100 feet. The rhombus forms an open atrium. If you're not familiar with what an atrium is, it's typically an opening in the center of a building. They usually have trees or plants, or typically if you have a glass elevator, that's usually where it is. It's in the atrium. The rhombus forms an open atrium with diagonals of 50 and 25 feet. And when we get to the problem, okay, you'll understand how that's going to impact the building. Okay, again, composite of semicircles, rectangle, and rhombus. The dimensions of the rectangle are 125 feet by 100 feet. The rhombus forms an open atrium with diagonals of 50 and 25 feet. That little comment there about the rooftop and the lights, you'll understand that more when we get to the questions. The final building we are looking at is parallelogram shaped. It has a longer base of 175 feet, and a height from the longest base is 150 feet. Further, we're provided with information that the base angles of the parallelogram are 80 degrees and 100 degrees. So again, a parallelogram with a longer base of 175 feet and a height to the longer base of 150 feet. Base angles of the parallelogram are 80 degrees and 100 degrees. Now, we're going to be doing several calculations in class, and what I want is, since this set of notes is just about done and is very short, you are going to work a couple of these out before we actually get everything all going here. Okay, so here is the setup of the problem. The roof line of each building is to be outlined with lights. So we're doing some Christmas decorations or something like that here. If a strand of lights covers 16.5 feet, how many strands of lights will be needed to outline all of the roof lines of the downtown city? Okay. We're going to round our answers to the nearest whole number to keep things as easy as possible. And if the rooftop, well, we'll get to that here a little later on. If the rooftop of each building was doubled in size, how would it affect the number of strands of lights needed to outline the roof lines? Explain your reasoning. Okay, that's a different question. I didn't realize that was still on this paragraph. Okay, but anyway, there are 6 questions regarding this scenario that are looking at you right now. Okay, we need to know the perimeters of each of the 6 buildings. The perimeter of the hexagon building, the composite triangle trapezoid building, the circumference of the circle, the pentagon, the composite semicircles and rectangle, and rhombus atrium, and then the perimeter of the parallelogram. I want you to select any 2 of these buildings, and I want you to answer. Okay, so you're going to answer 2 of A through F. That will be checked upon entering the class on Monday, and it will be considered to be part of your notes. You will have the remaining 4 perimeters plus some additional questions to answer in class on Monday. But at any rate, that is the end of the notes. So hope you enjoyed some short ones. Take about probably another 10 minutes and calculate your perimeters of at least 2 of these. If you want to do a couple more, that would be fine as well. Anyway, we'll see you in class.